Okay, today we're going to look at two tests called the comparison tests. One is a direct comparison test, the other is a limit comparison test. But what we're going to be doing is comparing two series together. One that is a known series, we know whether it converges or diverges, and one that is our unknown series that's going to be our problem type, our problem that's given. And what the first test says for direct comparison, it says that if you're given two series, then if you can get them to line up, and this is kind of my notation for it, but less than a convergent converges and more than a divergent diverges. So if we're comparing a series that we know converges and we have another series that's smaller than that, well, if our series is small enough to converge, then anything smaller than that is small enough to converge as well. And then on the flip side, if I have a series that I know diverges, it's too big, it diverges, anything bigger than that is also going to diverge. So I'm less than a convergent converges and more than a divergent diverges. Now the hard thing with this is going to be what to compare it to. So I've told you you're always going to compare it to either a p-series or a geometric series, depending on whether you have a polynomial or whether you have an exponential, okay? So let's look at an example for direct comparison. So on this first one, we have the sum from n equals 1 to infinity of 1 over n cubed plus 1. So this one is, if I were to cover up that plus 1, 1 over n cubed is a p-series, where p is equal to 3. So that's what I'm going to compare it to. So I'm going to compare to the sum of 1 over n cubed. Now with 1 over n cubed, p is 3. We learned last class period if p is greater than 1, then it converges. So this one converges. So what I need to do is to get mine smaller than a convergent. So if I compare 1 over n cubed plus 1 to 1 over n cubed, what is adding a plus 1 on the bottom do? Well, it makes the bottom of the fraction bigger, which in turn makes the overall fraction smaller. So this is less than something that converges. So if we're less than something that converges, then our series converges by direct comparison. Okay, this one is known that it is small enough to converge. So if this one is even smaller, then it's also going to converge, right? All right, looking at this one, again, if I were to just cover up the plus 2, I have 2/3 to the n. That's a geometric. So that's what I'm going to compare to. So I'm going to compare to the sum of 2/3 to the n. Now this one, the ratio is less than 1, so this one is a converging series. So now I've got to look at how mine compares. So I have 2 to the n over 3 to the n plus 2 compared to, if I want to write it as 2 to the n over 3 to the n. Now again, adding 2 on the bottom makes this fraction smaller. So we are less than, so we are smaller than something that converges. So we converge by direct comparison. Okay. All right, let's look at this one. We have 1 over the square root of n minus 1. Again, by just covering up that minus 1, that's a p-series. That's 1 over n to the 1/2. So that's what we're going to compare to. So we're going to compare to the sum of 1 over n to the 1/2. This one diverges, okay, because p is less than or equal to 1, so it diverges. So what we're going to do is we're going to compare our 1 over the square root of n minus 1 to 1 over the square root of n. This time I'm subtracting 1 from the bottom. That's going to make the bottom of the fraction smaller, which is going to make the overall fraction bigger. So now we're greater than the one we're comparing it to. So bigger than a divergent diverges. So this one diverges by direct comparison. Now, most people at this point ask, what if you can't get it to line up? What if you get smaller than a divergent? Well, typically that means you need to flip to this next test called limit comparison. Okay, either that or you're using the wrong series to compare it to, or the wrong test. Okay, so but typically if you can't get it to line up, then you need to flip to limit comparison. So on limit comparison says if we take the series and a series that we're going to compare to, so we're given 2 series, okay, the problem and then the one that we're going to compare to. If we do the limit of those 2 series as we go to infinity, and we come up with a number that is any positive number, it needs to be finite and positive. 0 does not work. 0 is not a positive number, okay? Then they will match in convergence or divergence. So if the one you pick converges, then the problem will converge. If the one you picked diverges, then the problem will diverge, okay? And these we always find to a p-series by reducing the highest exponents on top and bottom. So we think about limits at infinity, and we think about our largest term on top and our largest term on bottom. We're going to look at those largest powers and we're going to compare and reduce. And that's going to be what we compare to. So on this one, this first one, we have 1 over 3n squared minus 4n plus 5. So we're going to look at the largest term on top, which is 1, the largest term on bottom, which is 3n squared. So we're going to compare to the sum. We're not going to worry about the 3 of 1 over n squared. Okay. So all I did was take the largest powers on top. Don't worry about coefficients. That's just extra stuff to worry about. All right, so what do we know about 1 over n squared? It's a p-series with p equal 2. That's greater than 1, so this one converges. All right, so what we need to do is the limit as n goes to infinity. Now, let's go ahead and always put the one we're given on top and the one we're comparing it to on bottom. It does not matter. I would just be consistent. So I am going to put 1 over 3n squared minus 4n plus 5 all over 1 over n squared. So this is the limit that we're looking at. So now I need to flip and multiply. So that's the limit as n goes to infinity. If I flip and multiply, I end up with n squared over 3n squared minus 4n plus 5. Now I've got an equal situation, so this limit at infinity is going to be 1/3. Now, last I checked, 1/3 was a positive number, so that means my series are going to do the same thing. They're either going to both converge or both diverge. Since what we compared it to converged, our series is going to converge. So we can say converge by limit comparison test. Okay. All right, this one we have 1 over the square root of 3n minus 2. So if I look at largest thing on top, largest thing on bottom, I'm going to compare to the sum of 1 over the square root of n. Now again, that's a p-series where n is 1/2. So this guy diverges, okay? So let's do our limit. So we have the limit as n goes to infinity. Again, I'm going to start with what they were given on top. So 1 over the square root of 3n minus 2 all over 1 over the square root of n. Then I'm going to flip and multiply. So I have the limit as n goes to infinity of the square root of n over the square root of 3n minus 2. And so then I've got, again, another equal situation. In this case, my ratio is 1 over the square root of 3. Didn't say it had to be a nice number. It just has to be positive. That is a positive number. So then they're both going to match. So since what we had diverged, we are going to diverge by limit comparison. Test. All right, and it's as simple as that. So those are our next two tests. We have 2 more that are coming next class period, and then we'll put it all together and see if you can pick out which one is which. If you have any questions, come see me. Bye, guys.